Hi all, till now we have studied about the steady state heat transfer and also the case of steady state heat transfer when there is internal heat generation inside the body, and we have seen for the case of plane wall, solid cylinder and solid sphere, and we have also looked upon how to derive the temperature distribution starting from their governing equations. And from now on we will take this series to forward, and in this lecture we will start about the unsteady state heat transfer. So from the previous lectures we have seen that for any body in which heat transfer is taking place, if we have to define the temperature at any particular point, we have to define the temperature in terms of its location as well as at which particular time we are interested in finding the temperature at this point, right? So to specify temperature, if I want to say that at this location A this is the temperature, so you should ask that what is the location as well as what is the time, means at what time this temperature value is there in the body. So if temperature variation in the body not varying with time, if temperature variation is not there with respect to time, then it is called steady state heat transfer. But if the temperature variation is there with respect to time, then it is called unsteady state heat transfer. That is what we are going to study, right? So unsteady heat transfer has numerous applications in the industry, like cooling of IC engines, heating and cooling of metal billets, and heat treatment processes that are done in the steel industries, right? So if temperature variation repeat with respect to time, if temperature variation like repeat with respect to time in the body, then it is called periodic unsteady state. Periodic unsteady variation, right? The examples of periodic unsteady variation are heating of ingot, cooling and heating of IC engine. All right. Cooling or heating of IC engines, and building, right? Building any house, it is subjected to a heating in the daylight, and in the night it is cooled, right? So it is done after 24 hours, so it is periodic unsteady state variation of temperature. Next is if the variation of temperature is time. This is just a qualitative graph, this is not quantitative, it is not up to scale. And if the temperature variation is like that or like that, if it is constantly decreasing or constantly increasing, then it is called unperiodic or non-periodic. Non-periodic unsteady variation. Unsteady variation. Right. Variation, right? So examples are like heating of ingot, heating of an ingot in a furnace, all right. So now in the case of unsteady state heat transfer, there are few numbers which are very important and which are necessary to understand before starting the analysis of unsteady state heat transfer, right? The first number is, yes, Fourier number. So what is Fourier number? Consider this a representative body, like it has length, breadth, height, everything is L. Okay, just for the case of simplicity and for understanding, and suppose it is dipped in some cold fluid, right? These red color dots are representing the cold fluid and it is very hot. This is hot body, all right. So what is happening, and this body is suddenly dipped inside this cold fluid, right? So what will happen, the heat that is stored by this body will come out, right? So first the heat will be coming out by conduction, and then then by convection to the cold fluid outside, right? So whatever the stored energy is there, that is coming out by conduction, okay, to the outer surface. Okay, so this ratio we are interested in is what is this ratio? The conduction heat transfer in a given volume and to the heat stored, rate of heat stored in a given volume, and that heat stored in the body is going to decrease with time, right? We are just interested in the magnitude in a given volume, all right. So we can write the for conduction we can write like from the Fourier law, like Ka delta T by L. Okay, delta T is the temperature difference between the inside surface and okay, between the inside surfaces, and stored energy, we know that stored energy can be written by mc del T by del T. So writing the average derivative rho vc times delta T by time. So if we write A as L square and volume, the body as L cube, and by simplifying we can get alpha T by L square. How? K L square, A is A L square delta T by L upon rho times C times L cube delta T by T. So if we simplify, this is C and alpha is nothing but thermal diffusivity, right? So we get this ratio. This ratio is known as Fourier number. Okay, so Fourier number represent that in which body the heat transfer will take faster or slower. Okay, so it decides the thermal response of the body, decides the thermal response of the body. Higher Fourier number means faster will be the propagation of heat inside the body, right? So if we nail down this Fourier number as alpha is k by rho Cp times T by L square. So if k is higher means Fourier number will be higher. It means it will take less time for the body to change its temperature, right? If the temperature is changing with time, all right, and less time required for the body to change its temperature, and the depth to which the heat can propagate inside the body will also be higher if thermoconductivity is higher for the given time. Okay, for the given time the heat can propagate inside the body for longer depth. Okay, so if you think alpha is k by rho Cp and Fourier number is alpha T by L square. L is nothing but the characteristic length of any body. For our case this is Q, so this is L only, but we will see that how to find the characteristic length for any body. Okay, so alpha and Fourier number have the same physical significance. Both represent that means how fast the heat will propagate before it get absorbed inside the body. But the difference is alpha takes care of only the properties because it is made up of only properties, but Fourier number take care of property as well as the geometry because it has characteristic length in its formula. All right, and mind that this ratio LC square by alpha is called diffusion time. Diffusion time means how much time it take for the heat to travel from this point to this point in the body. So you can see by intuition that if diffusion time is less means alpha will be higher, or characteristic length of the body is small. So if characteristic length of the body is small, then it will take less time for the heat to diffuse in the body. Okay, so in the next class we will see about the Biot number.